So when we take a look at specific gravity, also sometimes known as specific density, it's compared to the density of water. And even though the temperature of water will change its density, and that's the density of other hazardous materials, we still use it as a starting point. So most of your hydrocarbons are lighter than water, and that's why they float on top, and you can see the water burning on top. And other products are heavier on water, then they fall to the bottom. And if it's about the same specific gravity as water, or it mixes with water, then it mixes inside the water column. And this helps us know when and how we can respond properly, right? So we don't want to try to sorbent something up off the top of the water if it's not floating on the top of the water. So these are why these properties are important to know, so you can take a look at them. And at a glance, that's why I really like this, is because at a glance you could see something, right? So we both see that both benzene and copper fume have about the same molecular weight. Although this is a fume, so it's a finely dispersed particle, and this is a lightweight liquid. This is insoluble in water, where this is slightly soluble in water. Copper fume does not have a lower or an upper explosive limit, where you can see that benzene does. But here are specific gravities, so our benzene will be at the top of the water column and it will not mix. And here copper fume would actually be at the bottom of the water column. And again, it would not mix. So we could learn lots of things by just looking at our pocket guide and the properties of hazardous materials. And really the chapter in the text is one of the best chapters to really get your hands around this information if you're not familiar with the hazardous materials terms that we're using. So solubility in water is just the material's ability to dissolve into water. So some waters dissolve well, and some agents dissolve well in water and some don't. But it's really important to know if an agent is not soluble in water, then using water to rinse it away would do no good. And as gasoline floats on the top of water and it's not soluble, when you put water on top of it, it can actually spread the flames, and that's why we use a foam with gasoline fires. And miscibility is the ability of liquids to dissolve into a uniform mixture of any type of ratio. So just understanding the different types of properties of hazardous materials helps us understand how they're going to behave and what their volatility truly has to do with. So the flash point and the ignition temperature. So the flash point is just that minimum temperature in which there's enough vapor that the liquid can ignite, and so it flashes off. But combustion will not be sustained without fuel and some kind of sustained chemical reaction. And the ignition temperature is where you'll get a sustained burn without any outside ignition. That's the auto ignition temperature. So you could see that for diesel fuel, it's slightly lower than it is for gasoline, as it is for jet fuel, which means it's burns much more readily. The value of pH cannot be understated. If something is an acid, it tends to burn things away, right? It could etch into glass. Acids will do that. Now if something's a base, bases will melt. They melt things, they dissolve them. So a lot of household cleaners are bases. So here we have our bases with our really high pH, and here we have our acids with our really low pH. But one thing that you can see here is when you go from one pH to the number, it's not just a one step change. So when we go from a pH of 7 to a pH of 6, there's actually 10 times the acidity in urine than there is in water. And we use water as the pH of 7, where it's considered neutral. So between 6 and 8 are pretty neutral pHs. Acids and bases are stored separately. When mixed together, they can create exothermic reactions or other types of reactions. So this is one where the Department of Transportation calls them all corrosives, but they're different types of corrosives. So we have our acids and we have our bases. And the abbreviation for pH is potential hydrogens. How many hydrogen concentrations do we have when we compare that to our distilled water? So urine has far more hydrogens on it than pure water, whereas toothpaste has less acids and bases. So the next one we use more so in detecting the presence or how much of a certain hazardous material is in the environment. If it has an ionization potential, most VOCs, volatile organic compounds, have an ionization potential, which means that they will readily burn. And we can use this to evaluate how much of the material is actually in the environment when we have a photoionization detector. And so the definition, or the easy definition, is how much energy, how many electron volts does it take to knock off an electron, and that number is specific to the agent. And once you get the right lamp and the right ionization potential number reading, you can see not only how much of something is in the environment, but also with the right PID meter, what exactly that agent is in the environment. Flammability range or explosive limits, they're kind of misnomered when we call them explosive limits, but it's the minimum and the maximum concentration at which something will burn by percent volume in air. And so this percent volume in air always is a little difficult to understand, but we're just going to make it really simple here. So here we have the percent of ethanol that's in air. So its lower flammability limit is 3.3. So at 3.3%, ethanol will burn in air. And at 19% or over 19%, it'll be too rich and it will not be able to burn. So if you have too little of something, it won't burn, and too much of something, it won't burn. And this denotes the flammability range. So we try to operate really close to the low end of the flammability range. And you may have heard that when you set your combustible gas meter, you set it to 5% of the lower explosive limit. So how are we going to take a look at that? So let's just take a look at some numbers. Okay, so all your meters need to be calibrated to a very specific gas. So you can't set something to 10% of the lower explosive limit of a gas, because we don't know what that gas is. As you can see by all of these gases, they are all quite different. So methane is between 5 and 15%. The lower explosive limit is 5 and the upper explosive limit is 15%. So if we're going to calibrate our gas meter to 10% of the lower explosive limit, we would calibrate it to 0.5% methane in air. Same holds true for isobutylene. You can see that the lower explosive limit is really low, only 1.8% in air. And if we multiply this by 10%, we can see that we would calibrate our meter to 0.018% of isobutylene in air, which would be 10% of the lower explosive limit. And so how do we convert that to parts per million? It's really simple. We just multiply each 1% by 10,000. So let's look at our example here for benzene. The lower explosive limit is 1.2%. So 10% of 1.2% is 0.12%. Then we multiply this 0.12% by 10,000 and we get 1,200 parts per million. So the lower explosive limit of benzene is 1.2% in air, which doesn't tell us a whole bunch, but at 1,200 parts per million, then there's enough benzene in air to be flammable. Now, since the threshold limit value, or the TWA, is 0.1 part per million, it would be toxic before it would be flammable. But don't confuse these two. And one thing that really is important to remember here is that your meter needs to be calibrated to something specifically. And it's usually 10% of the lower explosive limit. That means we're so far away from the lower explosive limit that we have no chance of having an explosion when people are inside of the atmosphere. Sometimes different percentages can be chosen, but that's typically what we use for hazardous materials. Confined space evaluations. Now this is one of the most interesting things about hazardous materials. You have a boiling liquid expanding vapor explosion.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly, with little warning.
So as we can see from the video, when you have a gas that's in a container, a closed vessel, and it's exposed to heat, the pressure inside the vessel causes all of this vapor pressure to build up and can cause this boiling liquid expanding vapor explosion, which can be just create fireballs, as you've seen, and you can see some other ones. It's probably one of the most dangerous situations you can get in when you have a closed container that you can't remove from the fire or have no other way to at least cool it down to stop the vapor from building up inside, and then at some point it causes the mechanical failure. And so this is your moment of Zen. That means we've made it all the way through hazardous materials chemistry. It's just a brief chemistry introduction related to hazardous materials. I really like the book because it's kind of back of the envelope, but things that you can really remember. And this is a picture of my son in 2016, and now he has a mustache that looks a little bit like that. Have a great day.